Thank you, Ilya. Thank you, Nigel, and also the COSIC lab for having me. I'm going to talk about privacy enhancing technologies in general, a little bit at the beginning, and also talk about some of focus more on my work done during my PhD. Feel free to ask questions during the talk and interrupt me. And with that, I'll get started. I'm going to start by just acknowledging it's always a team effort. There is a whole bunch of people who've gone behind a PhD, I think. And so I'm going to in particular highlight Nishant and Divya, with whom bulk of the work which I've done started. There's a bunch of people from Leuven here, Raghav being one of them. Okay, so I think over the last few years we have seen an explosion of technologies such as email, technologies such as social networks, or in general location-based services as well. All these technologies, central to all these technologies is user data. This has led to the rise of massive amounts of data collection. It has also led to a number of technological advances which use this user data to improve the services. And finally, it has also led to a number of privacy concerns about the data collection as well as these advances. So what privacy technologies in general do is to enable the data collection and such technological advances in a manner that is privacy conscious, or at least knowing what are the consequences of that. So I'm going to start off with what a privacy advocate's toolkit looks like. So we have a number of technologies which we like to throw at these problems, and some of them are noted here. And I'm going to briefly talk about each one of these technologies, just very, very briefly for the sake of the breadth of the audience. So I'm going to consider this a very simple toy model for privacy computation, in the sense that you have a user who has some data which is very personal to it, and then you have some centralized entity who would like to compute data with or also deliver some service. And we are going to look at what happens in the world today. So the user simply sends their data across to the centralized entity, and in return to that data, the user gets back some service. So it could be a location-based service, it could be just any kind of service. So we look at privacy technologies from this lens, where how do we actually apply these technologies to this simple problem and sort of enable the same technology but with some privacy on it. So I'm going to start with homomorphic encryption. So homomorphic encryption changes this paradigm in the following sense, that the user has the data, but they can locally encrypt it. So they just generate a key, encrypt their data, and then they send this encrypted data across to the centralized entity. What happens is this is encryption in the standard sense, so as long as the key does not get delivered to the centralized entity, the data is really not accessible to the other entity. Homomorphic encryption is a very specific form of encryption where now you can actually use this encrypted data and do computations over it. So that's the big paradigm shift which homomorphic encryption brought, that you can actually have encrypted data and perform computations over it. Once you have that, what you can do is you can do the computation and then send back the response. And what this is still encrypted with the user's key. And so now you can just locally decrypt the received response, and then you can have the transformed data or the service. So that's one very interesting technology, which is homomorphic encryption, that kind of solves this problem and can be used in many other ways. The next one is multi-party computation, which is, again, one of our favorite forms of computation. So multi-party computation addresses this issue of privacy in a slightly different sense. It uses a non-collusion assumption, so it assumes that you have a number of parties, like not one centralized party, but a number of them, and you trust that not all of them will collude with each other. So they won't just join hands and they're like, okay, let's get the data. So in this setting, what happens is the user can somehow split their data into different parts and share the parts of this data with each entity. And this has to be cryptographically secure. It's not just taking an image and splitting it into left half and right half and sharing. So that's what you do. Now it becomes a distributed function computation problem, where now these users have some parts of the data and they want to compute over the underlying data in a manner which preserves privacy. So it's a distributed computation problem with more additional privacy properties in there. And once the function computation has been done, you send back the result to the response or the response to the user in two different parts. And now the user can locally reconstruct those to get the appropriate response. So that's how MPC solves this problem, where you really rely on this fact non-collusion and then use that to do the computation. These are, in my opinion at least, these are slightly different techniques, like the first two, homomorphic encryption and multi-party computation, because the privacy guarantees come from really the privacy guarantees of like conventional crypto, so assuming underlying hardness problem and then guarantees of that. There are other notions of privacy such as differential privacy. So this is the semantic meaning of privacy also has been well studied, but it's a slightly different notion. It assumes that the decentralized entity has a whole ton of data collected already, and one of those records corresponds to a particular user. What differential privacy allows another entity, like let's say an analyst, to actually query this data set, and so you can query this data set, get back some utility out of it. And what happens is differential privacy is, it can be used to quantify privacy in this setting where the response given by the server can be, it's given in such a way that it doesn't really depend on any individual user's data record. So in this case, this red record, let's say, belongs to a particular user. So the privacy guarantee to the user is given that if that user's data wasn't in that record or it was something completely different, the response is still going to be kind of similar, or like the distributions are the same. And so that's another notion of privacy we have, which is given by differential privacy. Finally, lastly, I'll talk about trusted hardware. So this is also a very emerging paradigm where privacy is derived from a very different part, which is you assume some piece of hardware is trusted, and then you build systems up from that point. So you just assume a small piece of a system which is trusted, and then you want to do everything else built based only on that trust assumption. And so in this case, you can assume that it's almost like you have a friend inside this centralized entity, and then you send your data encrypted with the secret key of that friend. And so only the friend has access to your data. And then they can compute on that, and then they can encrypt it back and then send it to you. So this is in some sense similar to FHE, but very different paradigms. But it allows you to just have complete privacy between the user and the centralized entity. So with that, if there are no questions, I'm not going to talk about federated learning just in the interest of time. I'm going to move on to more privacy. So over the course of my PhD, I had the privilege of working on a number of these problems. So privacy is very complex, many different aspects of it. And in particular, I'm going to actually talk about this space of private machine learning. So you tie the application to be machine learning, and that's what you want to do in a privacy preserving way. And so I'm going to in particular talk about this word SecureNN. So this is the brief talk outline. So I'm going to first talk about what are the challenges of multi-party computation based private deep learning. Then I talk about the SecureNN framework and some of the core components of that. And then I just quickly talk about the evaluation on like the experimental results, and then conclude with some future work. So a quick a slightly different take on MPC. So this is the traditional machine learning setting where one centralized entity has a lot of data, and then we are interested in computing some function of that. So here machine learning algorithm itself is seen as the function computation. So it could be SGD or something similar. And so that's the function computation, which is on this underlying data, like which is, let's say, very sensitive. MPC changes this paradigm where now you have split data, so you have a number of parties. In this case, we look at 3, and they jointly want to compute this. So the first thing is the user data has to still be shared among the parties. So if there is no data, then what are we really computing on? So that's where we have some constraint of this form where the user's data is really there somehow encoded in this shares. So that's some kind of constraint. And then the function computation problem actually becomes a distributed function computation where you want to really compute the same function, except now you just have pieces of that. So that's from a security point of view. So this is from a machine learning point of view. So let's say you talk to a machine learning person, and that's how they see a neural network. So this is a simple architecture, and this is what they want to train. So how do you really go about training such a network? So the first step is really to break down into different components. So let's say you want to do convolution, matrix multiplication, and so on. So you really break down the architecture into that form, and like most other computing infrastructure, we develop it in a modular form. So if you want to do convolution in a privacy way, you call a private convolution function, and then you call a private matrix multiplication, and so on. In particular, I'm going to focus a little bit on the nonlinear function because that's where most of the technical novelty of this work is. So ReLU is a very widely used function in machine learning. It's a very simple function. It looks like this is the graph. So if you have a negative number, you just make it 0. If it's positive, you keep it the same as the input. And this is notoriously hard and also leaves a lot of room for creativity, but this is very, very central to machine learning. If you want to enable machine learning in a private way, we have to come up with efficient protocols for this. A related neighbor is the derivative of ReLU protocols. So if you focus on problems which also involve training of machine learning algorithms, you want to be able to also have efficient protocols for the derivative of these functions. So that's the derivative of the other function. So in particular, we'll focus some of this central part of this talk on this on seeing efficient protocols for this. So let me talk about what are sort of the state-of-the-art approaches to machine learning and also how do we go about it. So yeah, so the key takeaway here was really that exact ReLU computation has been notoriously hard and it's difficult to do in this MPC setting. And so we really want to improve the performance of this. So this is a slide I borrowed from Dragosh, and so this is what state-of-the-art MPC protocols look like. So there are different types of sharing schemes. So there is secret sharing, which is arithmetic kind of secret sharing. You can also have Boolean secret sharing, and then there is garbled circuits, and both of them have their own pros and cons. So if you have a constant round protocol, you are better off like using garbled circuits, or you want to use garbled circuits are constant round protocols, and so you kind of just do it one shot, whereas secret sharing schemes are round dependent, so it depends on the size of your computation. And they are also better suited for certain domains. So arithmetic and so secret sharing can do arithmetic Boolean circuits, and they are good for certain types of function computation. Garbled circuits are better for certain types of computations as well. So what state-of-the-art protocols really do is break down the set of functions you want to do in the neural network into categories. So if it's linear functions or matrix multiplication convolution, you're better off using arithmetic circuits to actually do these function computation. On the other hand, if you want to do these nonlinear functions like ReLU, maxpool, and so on, you're better off using a Boolean secret sharing scheme. And so what all these protocols do is use some kind of interconversion protocol. So you start off from arithmetic secret sharing, you do the function computation, and then you move to a Boolean secret sharing kind of way, and then do the ReLU protocol very, very fast, and then come back. And so that's really what these protocols are doing. One of the biggest insights in SecureNN is that we can actually eliminate the need for these interconversion protocols. So the reason why these interconversion protocols, you want to eliminate this is because they have at least a minimum amount of computational expense or like communication or some kind of overhead, where it really, converting between these really requires you to either do some kind of bit extraction, or because these are functions of the bits of secrets, whereas this is really a function of the entire number itself. And so you have to do some kind of thing, and there you really have you can't push the performance beyond a certain limit. And so there is some benefit in really eliminating this, and so you can really start pushing the performance of these protocols. So is SecureNN yet another MPC protocol? And so I'm going to defend it with sort of three points. I don't know why Dragosh is laughing. But the first one is it introduces fundamentally new techniques, and so I think that's always a good thing for a field where you can now sort of use these techniques in different places. So in particular, we eliminate both oblivious transfers and garbled circuits, and that really is where most of our performance improvements come from. The second one is closely tied to that, is really that the ease of use. So this SecureNN at the core really relies just on modular arithmetic. So it's just adding two numbers modulo certain modulus. And so that makes it really, really easy to implement. So if you take the core protocols, you can actually implement, and just looking at the paper, you can just write the code in Python once you have like the rest of the infrastructure. So it's really easy to implement. It also is an important design point because it makes, it reduces the barrier for having a non-faulty implementation where your just primitive set is really simple. And finally, SecureNN is fairly fast. Like it's communication efficient as well as like we implement it and see the performance improvements in practice as well. So with that, let me dive into the SecureNN framework itself. So the system design is, we are stuck to a three-party model, so it's very specific to a three-party model. It's a semi-honest setup. It's a very, very weak adversarial model. So semi-honest is where every party will follow the protocol and then try to extract as much information as possible following the protocol. The second thing is we rely on arithmetic secret sharing. So whenever, in particular, it's an asymmetric protocol. So there are two parties, and then the third party is slightly different in terms of its functionality. And when we say arithmetic secret sharing, so if A is the secret, you have two parts of the secret which are just uniformly random in the space. And the choice of this modulus is also very specific, because when you choose this particular modulus, function computations become really fast, because you don't really have to take care of the modular reductions here. Whereas if you use a general purpose number theoretic library or just any other modulus, you really have to, whenever you add two numbers, you have to see if they overflow the modulus and then reduce it accordingly. With this, if you just implement it in C++, all of that is taken care of naturally. So there is a lot of benefit to using it in this particular modulus. We have an invariant where all the functionalities we define, like the input and the outputs, are just 2 out of 2 secret sharing, and so they are basically in the same setup. So the secret input A is actually secret shared between the two parties in this form, and similarly the output is also secret shared in the same form. So that would be one functionality. And finally, we prove the security of our results in the UC framework. So all these different components, we show them are individually UC secure, and so the framework allows you to arbitrarily compose these and argue for the security of the end-to-end protocol based on the security of individual blocks. So with that, I just come back to this. So this is in some sense what we are aiming for. Like, we want to train such a network. This is the set of functionalities we want to enable. And let's take a look at this particular functionality. By ReLU, I mean actually the derivative of ReLU. So this is one of the core building blocks of this entire architecture. So here I have a quick diagram. So the input is shared between the lower two parties, and this is what we have. The output here is actually going to be a single bit, which will be shared across the two parties again, and that output bit is actually the derivative of ReLU of the input. So we do it in a series of small steps, and each one of them is, it just helps us reduce the problem to a simpler one. So the first one is really changing the LSB. So computing the derivative of ReLU is the same as computing the MSB. So that's the first insight. And it's not too hard to see. For that, I'll just give a quick intuition. So this is the space of all our input values. And so we have a 64-bit range. This should be to the power 64 minus 1. But you have this range, and what we have is the derivative of ReLU. So you use fixed point encoding, where every number has a finite amount of floating precision in some sense, and so we use that, and we use the native C++ encoding. So you just use uint64_t as your data type, and then these numbers are just positive in that sense, and the second half is negative numbers. And so in that sense, it's really easy to see. So the derivative of ReLU of positive numbers is 1 and negative numbers is 0. And the MSB of the first half is 0 and the MSB of the second half is 1. So they are just related by 1 minus. So that's the first thing. We haven't really reduced the complexity of the problem itself, because we just reduced this problem into finding something else which is equally hard. In general, MSB computation is really a function of all the bits of the shares, because you could have like bits adding up and then carrying over. And so the MSB is really a function of all the bits. So the second insight here is that computing the MSB is easier if you have shares in an odd modulus ring. So if instead of starting from here, if we started from some random shares except in an odd modulus ring, so you had a different ring there, then this function computation is fairly easy. And the reason for that is, again, I'll bring this problem here, where you can convert an MSB problem into another LSB problem, which is of some simply related input. And to see that, again, I have some quick visuals. So the MSB of the first half of this range is 0. And so let's consider an input which is within that range. So when we look at the input twice of that, it's going to span the entire range of numbers. And it's going to be an even number in the sense that the least significant bit of this is 0. So LSB of 2a is 0 when a is in this first half of the range. And as you can see, if A is actually in the second half of the range, twice A actually overflows the modulus, and so when you reduce it modulo the modulus, you'll get an odd number in the sense that the least significant bit is 1. And so now we can use this as a distinguishing test between these two, where you transform an MSB problem into LSB problem of some other input. And LSB problems are easy because they only depend on the least significant bit of the shares, and so they are not really a function of all the bits. So in that sense, you kind of avoid the complexity of the MSB problem. So I think you might say that, okay, so this is also easy, so in that sense we haven't really solved the problem, so what's this missing block here? And so that's one of the contributions. So we introduce a primitive called share convert, where we actually show how to convert shares from one modulus to another. And this works in general, so this is not specifically to just converting between these two shares. You can convert between any two moduli. And that's what we call share convert. It's of independent interest. So, am I doing okay on time? Yeah. Okay, then I'll go into the details of the share convert protocol actually, because it's kind of unsatisfying to leave it here and say that, oh, that's where all the complexity is. So I'll go into details of how the share convert protocol works. Before I do that, I wanted to give this as well. So right now what we do is we take the input, we start from the input, then we apply the share convert functionality, convert shares into odd modulus, then we use the compute MSB, and what we have at the end is the derivative of ReLU. In general, we want to be able to enable a whole bunch of other functionalities as well, and they all kind of relate to each other from this core block, because the derivative of ReLU in a sense is a comparison function. And that lets you start doing all these other, like, so ReLU, for instance, is just taking the derivative of ReLU and multiplying by the input of the share and so on. So you can start doing all these protocols once you have the derivative of ReLU. And there is also matrix multiplication, where we use standard techniques. I think I also wanted to mention, won't go into the details of this, but derivative of max pool, at least in the semi-honest setting, you can do something really, some neat tricks there. And so we have that in the paper, but I won't really go into the details of those. So with that, let's dig into what the share convert protocol is. So this is again the share convert protocol. So inputs are in an even modulus ring, and then the output is in this other ring we want to transform to. And so what we do is we use a greedy approach here. So we start off from A0, A1 within the 64-bit range, and the output is where we want to be. And so we just use a greedy approach. We just say, okay, let's take the input and say that's the output. And so A0 and A1, just reduce them into the new ring. So if one of those numbers was 2 to the power 64 minus 1, you just make it 0. And so you just say like, oh, now let's see if this works. And it turns out this greedy approach is not too bad, like in the sense that if you have the two shares who are adding up to the secret without overflowing, then you're actually fine, because these numbers do end up with the shares of the same number. On the other hand, if you have overflow in the original shares, then you notice that the answer is actually wrong. You don't have correctness of this protocol. You might also notice that the answer is not too off. It's off by 1 bit because it's just really close by. And so that kind of points us to introducing this function, which is a wrap function. It's really a function of these two secret shares. So it's not a conventional functionality in the sense you just have it as a function of the secret. It's a function of the individual components. And it's 0 or 1 depending on whether you had an overflow or not. And so what we do is actually, this is what the share convert would look like. So you first securely compute this wrap function, which is a 0 or 1 depending on whether you had an overflow. And then you apply a simple error correction algorithm, where you take the greedy approach, where you have A0 and A1, and then correct it with this shares of the correction. So theta 0, theta 1. So let's look at how do you actually compute this shares of the wrap function, which is theta 0, theta 1.
Sorry, I have a question.
Yeah.
So why don't you then just use this wrap function as the most significant bit?
That's a very good point, actually. So this is kind of how this thing was invented. So that's in SecureNN. It turns out that you can actually optimize these, and wrap function essentially contains all the complexity of the derivative of ReLU. And so you can kind of actually do that directly, essentially. So that's some of the follow-up work I'm doing is really introducing that optimization. But yeah, that's a very good point. It's kind of going all around. But
I mean, it's just wrap of 2 times A, right? You just multiply by 2, and then it's just wrap of this guy.
wrap of, maybe I'm missing. So wrap of 2 times A is, you're saying the derivative of ReLU?
Was that not the same? Maybe it was.
Yeah, no, I think it is. Yeah, it is. And so, yeah, that's sort of the follow-up work is where, so I look at it in a slightly different setting, but yeah, the wrap of 2A along with, I remember the expression, maybe we can take it offline, but I think that's really it, like wrap of 2A along with some local computation does it. Like, so in the 3-party setting in the follow-up work, it's really like the MSBs of individual shares along with the wrap of 2A that really gives you the derivative of ReLU. So, but I haven't thought about it in this 2-party sort of 2 shares kind of scenario. But yeah, that's true. So, talk about how this share converter works. So we again assume shared randomness between every pair of parties. And so I have just flipped this diagram over. So these are the 2 computing or like the primary parties. So first A is really the secret on which we want to compute this. And R0, R1 are locally generated random numbers which are related by this equation. So it's R is effective, R0, R1 are shares of R, and they are accessible to both these parties. So that's the starting point. So what we do is, so the first party computes this alpha in the clear, like so it has access to alpha, which is this wrap function computed on R0 and R1. And this modulus L is effectively 2 to the power 64. We have written it for generality. So the interesting thing about this wrap function is really it lets you write an exact integer relation. So this is not true in the modulus sense, but this is true as an exact integer relation. So you add the 2 shares and then you subtract the modulus depending on whether alpha is 0 or 1, and that's R. So, and then it's the entire protocol is just a whole bunch of just doing these. So the second step we do is we blind the secret A with R. So essentially this party adds A0 and R0 to get something, and this party has A0, A1 and R1, and you add those 2 up, and so you get A0 tilde, A1 tilde, and these are not related to the other notation I introduced. So you have these 2 related by A0, R0, and the wrap bit is, now we call them beta 0, beta 1. Then now you can do this where you can actually send these 2 shares to the third party because the third party does not have access to the random blinding mask, and so you can actually share it with the third party. And now the third party can actually do this where it takes A0, A1, A0 tilde, A1 tilde, and then it computes this secret X and also computes in the process the wrap around there. So this right hand side is actually, so this is the protocol. This is something that will make seeing the correctness of this protocol simpler. So we can write an exact relation here as well. So this is the computation. Now X is in the clear with this third party. So what the third party can do is now actually send back shares of X to each of these parties, but we send them in a very specific way. So we choose a small prime modulus here, and we actually share the bits of X in this small modulus with these 2 parties. So effectively we have 64 bits of X, and we take each individual bit, and then we actually split into random shares modulo this small prime, and then give 1 share here and 1 share there. So now at the end of this, what these 2 parties have is a sharing of this number X, but sharing of bitwise bits of X. And then there's this subroutine which we call private compare. So private compare it's not too hard to see this. I won't go into the details, but private compare is essentially a comparison function, but it takes very specialized input. So in the sense that the previous way where we have shares of bits of a number in a small prime modulus, that's what is computed. And then we also have some public random number. So in this case, the R which we started originally with, that's the public random number. And what private compares allows us to do is really compare the secret value with the public number. So we invoke this private compare routine now that we have the input criteria met here, and we have effectively we can compute this bit eta, which is X greater than R minus 1. So where X is the reconstruction of all those bits. And then we can use this to actually write another sort of simple relation, which is, so I think this relation might be a little difficult to see immediately, but I think I do have a visual on it. So So first is X is simply just A and R, A plus R, because when you just blind them and add them up, so X effectively is just a sharing of A plus R modulo the modulus. And so X is effectively this is what the statement is saying, X is A plus R. And this wrap function, or like what is the carry bit, why is that actually equal to this X greater or related to that, like X greater than R minus 1? And the reason is fairly simple, because if you just look at this simple thing where you add two numbers and they either overflow or do not overflow in the modulus. And what you can do is if you compare X with R minus 1, it can really tell you whether there was an overflow or not, which is really what this part is trying to capture. In particular, if you take a secret A and take the random number R, if you add these two up and if it's to the right of R, then you didn't overflow. But if it's to the left of R, you had an overflow. And so effectively this comparison where whether you are to the right of R minus 1 or to the left really tells you whether you had an overflow or not. And so effectively this is really the intuition behind it, that the wrap of A and R is directly related to this comparison which we are doing here. And so that's pretty much it actually. So we just assume that this is the bit theta which we wanted to compute, and A is A0 plus A1, and like with this wrap bit theta, then you can see that if you just strategically add and subtract these relation, you'll get a relation between the Greek symbols here. So in particular, if you just do this 1 minus 2 minus 3 plus 4, this particular combination, all the other symbols just cancel out, and you have a constraint among all these Greek symbols. And if you see how we actually just trace this protocol, everything except this theta is known to some party or can be computed as shares. So you have beta 0, beta 1 computed by each of those parties, delta and eta already computed by either the third party or between the first two parties, and theta is what you are interested in. So that's how you really compute shares of theta. It's also useful to know that like none of these really reveal anything about how the secret. So it's always either blinded or XORed with something. So that's really the that's the secret sauce here. Like you throw in this. The other interesting thing is, if you look at the base of the computations in this entire protocol, it's just modular arithmetic. Like each party is doing is just computing wrap on something and just doing modular reductions, like maybe in a small prime or something else. And so it really makes it fairly efficient in terms of compute, as well as it really reduces the overall communication as well. So with that, I'm going to dive into some experimental results just to see how this protocol performs. First is this protocol is developed in C++. It's available open source at this particular repository. It's one-man effort, and so it's work in progress, let's say, or it's not the best code, but yeah, it's a work in progress. We also tested over both the LAN and the WAN setting, and so just trying to see how it compares in realistic deployment scenario. These are the network parameters in some sense. So, and then finally we tested over some small networks, and so we take some from the security community, also some from machine learning, and then see how the protocol performs over these. So I think this is the comparison of private inference. So you just run the forward pass of a neural network, and you want to classify a particular input. So we run it over different networks, and you can see that SecureNN generally outperforms most prior work by either an order of magnitude, like generally somewhere between, I don't know, 3x to an order of magnitude, I think. The other interesting thing is we really don't do an online-offline split in this case, like which can also be an interesting contribution, because you can really push the online performance further by offloading some data-independent computation. So yeah, the key takeaway is SecureNN is generally, depending on the network architecture and all those other parameters, it's hard to evaluate, but it's generally between 6 to 113 times faster than any existing approach. We also tried to run it, so back then there was fewer works in this space. So this is the comparison of private training, and so this is on a small network, but it's end-to-end runtimes of a network, and it's generally fast, I think. So this is a 2PC version, this is a trusted party aided, client aided 3-party version. And And I think SecureNN is generally faster in the WAN setting because we really strictly reduce the communication and as well as the number of rounds, and so the improvements are better in the WAN setting. In the LAN as well, it's fairly modest, and this really comes from a strict reduction in communication overhead. So when we look at the communication overhead of all these protocols, this is the minimum, like in theory as well. So that's also an interesting comparison point. And I think with that, yeah, I just wanted to talk a little bit about the impact. SecureNN already seen some deployments, I think, in different places, and so it's good to see that people are trying to adapt this into their work. And I think with that, I'll talk briefly about some of the follow-up work which I'm doing, or yeah.
On the previous slide, you had offline 0. What does that mean? Like, who's generating the triples?
We generate them using the third party. Okay. And then share it between the two, but we do it online. Like, so if you need a triple, you just do it. And so in that sense, yeah, that's something that definitely can be outsourced to the offline, as well as some of the other parts of ReLU as well can be really improved by.
If the third party generating triples, then if a third party and one of the other parties would break the security of the protocol, yeah?
Yeah, so this is semi-honest with just one corruption, yeah.
You don't have one corruption?
Yeah, only one corruption, yeah. We don't, yeah. Yeah, so that's, I have one point, I think, yeah, so I think this will bring me to really like this, looking forward. So this is, again, very weak adversarial model, like semi-honest, just one corruption. I'm working on making it secure in an honest majority setting, so making it maliciously secure. And it's also not very easy because SecureNN, if you have seen the protocol construction, it's very semi-honest. Like, it's really one party doing whatever it wants. And so it's not easy to actually make it maliciously secure, even in a single maliciously corrupt setting. I also wanted to mention, actually, SecureNN is, we also prove malicious security, but it's really the notion by, I think in a CCS paper in 2017, where you split the privacy component with the correctness component. So you can have privacy, but not have correctness in a malicious corruption setting. And that's what SecureNN also achieves. Like, you can have privacy of your data, but really not have any guarantees on the correctness. And so that's something to know, but it's not maliciously secure in the conventional sense that, like, the output, if there is no abort, the output is correct. So that's what one of the follow-up work is. It's also very interesting to consider the dishonest majority, which I also think is probably the most realistic deployment scenario. So I think a few open projects there would be, so we have one malicious corruption, so going from semi-honest to one malicious corruption, so that's one problem. Also going to a dishonest, what if you have two parties which are corrupt, like, can you still do anything here? Another interesting question is really to consider a two-party setting, like, is it possible to extend this to a two-party scenario, which is also very, I think, promising deployment scenario for MPC. So these are some of the open problems in the privacy space. There's also very interesting open problems in the machine learning space, where we have focused on CNNs, which is a class of neural networks, but it's just one class of neural networks. And there are a number of applications of other neural network techniques where RNNs, LSTMs, and you can just go on. And they require slightly different set of functionalities, which are, again, hard in MPC, but like, can we actually extend support to do these efficiently? So that's another line of extending this work. And finally, the integration with TensorFlow PyTorch, and it's that's a more bigger effort where you need a team of people. And I think SecureNN is being adopted by some of these big teams, so that's good to know. But really integrating it into, like, existing machine learning frameworks makes it much more user-friendly to machine learning experts who don't have to deal with the MPC backend. So I think, yeah, with that, I would like to thank you for your attention. And yeah, this is the broad vision here, is to really make private deep learning a practical technology. And with that, yeah, I would like to thank you for your attention.